University of Michigan and in the Faculty of Earthquake Engineering at IIT Roorkee. Sir has completed his bachelor from the National Institute of Technology, Tiruchirappalli in 1989 and MS from the University of Oklahoma, Norman in 1992. Sir received her PhD degree from the University of Michigan, Ann Arbor, USA in 1996. Sir has published over 150 peer-reviewed papers in journals and conferences in the area of structural and earthquake engineering. Sir has received John B. Scalzi Research Award in 2021 from the Masonry Society, USA. In 2000, Sir received Shah Family Innovation Prize from Earthquake Engineering Research Institute, USA for risk mitigation and retrofit. Sir has also been awarded the Young Engineer Award from the Indian National Academy of Engineering in 1999. Sir is also elected Fellow of the Indian National Academy of Engineering in 2010. Sir is the coordinator of the National Information Center of Earthquake Engineering at IIT Kanpur since 2009 and a director of the International Association of Earthquake Engineering since 2021. Now, I would like to invite Dr. Durgesh Rai, sir, to share his words of wisdom and experience with us. Over to you, sir.
Thank you. Thank you, Amira Sheikh, for the very generous introduction. And let me see if I can Is this visible now or? Hello?
Not yet, sir.
Not yet. Okay. So I'm saying that I'm sharing my. Is there somebody can help me? What is this thing?
Sir, just share your screen, sir.
The content only is that.
There are three dots on the MS Teams. Click on that three dots. Sorry, sir. There are up arrow on besides the mic.
In the share content, you have content only side by side.
Desktop, sir. Desktop or window.
I'm not getting that.
Screen share. There is a option of desktop or Windows.
Sir, there is a arrow open share tray.
Okay.
Yes, sir.
So, are you seeing the screen now?
Yes, sir.
Is it fine?
Yes.
Yeah, it is fine, sir.
Okay, good. Okay, so sorry for the disruptions, and well, let me again thank Dr. Singhvi for inviting me to speak at this, and also to Amira for the introduction. And the topic for this hour is about understanding the structural behavior through experiments in earthquake engineering. And what we are going to do in the next 60 minutes or so is to see that how, in engineering, we use the experiments to build the knowledge for which the analytical methods are not sufficient. Analytical methods are much cheaper, and the especially have become much cheaper because of the cheaper computing that is available nowadays. But then it's the tools that are there are not sophisticated enough to capture the physics of the real world. So we always have a need for the experiments to train our numerical models. So in that sense, we should look at the experiments, the a a supplement to the numerical, or to make our numerical simulations more uh, effective. And so in a way, that is how the engineering has worked, and we all are engineers. We know what the engineering means. Is basically, it means to create something. That is something what people write in the dictionary, that using the application of tools of related to mathematics and based on mathematical and scientific principle to practical ends. That we have a certain problem that we need to solve, and towards that we have to use whatever the mathematical and scientific tools that are available. And then we add on to other about the making it more economical, efficient, and so therefore we can do more than what in the resources that are available to us. But if you see that what engineers do, it's a little different than what is the literal meaning of engineering is. See, it's about, as they say, about art and communication, politics and finance, modeling and simulation, invention, approximation and measurement, and estimation, and more. So from our today's discussion, uh, the the tasks that are important for us is about modeling and simulation, and then approximations, because very rarely we know the entire physics of the natural phenomena or the behavior of the structures subjected to these environmental loads. Okay, and then the measurement. So these are the something what engineers do, and these are the three tasks that is something that we often deal with, in developing new theory or testing new design. So engineering, as I said, is a way to think about problems and seeking solutions. You need to define the problem and then trying to seek the solution in the. Now, coming back to earthquake engineering, if you see that what causes the earthquake, that is quite complex. Today, we understand that most of the earthquakes is due to the rupture of the tectonic plates. So this fault rupture, and there can be several, ways in which the fault can rupture, and therefore the energy release, would be very different. The waves that are generated are different depending upon the nature of the fault rupture. And then, of course, they travel to your site. So there is certain modification that happens in the wave as they pass through the interior of Earth, and when they come to the crust, you may have some soft soils which can further modify them, and that is the motion that gets delivered as a loading to your structure. So if you see, this is a quite complex process. We know very little here. We know very little about the interior, how this waves will be traveling, how they get modified, and what will be eventually delivered to our side. Unless I know that, probably I may not be able to design it adequately. And then there are, one which is on the rock outcrop, which are on the lake bed. Some could be on hill tops, hill slopes. The structure can be, very long, such as the bridges. So you may get different loading at different supports. So point is that the process of the ground shaking for which we need to design that structure is quite complex. And what we know about hazard, that if you're located in certain regions, the code may give you um, a maximum PGA, for which the structure had to be designed, associated with the response spectrum. So these are the two quantities that you need to fix your forces. So currently we have been having this so-called deterministic or judgmental based zoning map. Now we are also working on getting the some probability based hazard maps, and something like a return period of 2,500 years, so you can get, and people have worked also in the past to get a more PGA in a different, using different methodology, different inputs. So with the time, of course, if we know more and more, these maps actually get updated. And in some places where you have more data, like in California, you can be more precise, telling that what is the probability of an event occurring in the next 20, 30 years, which has the certain probability of accidents. So point is again that there are a lot of uncertainties. Even if I choose a PGA, no matter where, there is a certain amount of uncertainty associated with it. So hazard is known with a lot of uh, uh, uncertainties, and then we have the structures that we build, in there, and if they are not up to the mark, so that we represent as a fragility. So risk that we define is that what is the probability that a structure that you build will survive a given earthquake is kind of a product of these three things. So we cannot do very much here. We still have to build the structure, but the only thing that we can do is to build them right. So here are some examples. Like this is the base isolated hospital built in Bhuj after the 2001 Gujarat earthquake, and we hope that in future it will do much better than the older hospital that did in 2001. And here is this gas pipe, oil pipeline in Alaska, which was built in 1960s. And here is a fault that this pipeline crosses. And the design was that we can take this pipeline over the ground and then put in on rollers. So during the fault rupture, this pipeline is so flexible that it can just roll on laterally on the rail and can accommodate this fault displacement. And so that was the design based on some scientific principles and also a guesstimate of what would be the probable displacement, at this fault, or whatever the knowledge that was available. And in 2000, there was a really earthquake on this fault, and it moved, and the pipeline worked pretty much as expected. So this says that, if we understand, if we build it right, even though there are a lot of uncertainties about the ground motions, we can still design safer structure. So this is, you have already seen in many earthquake resistant design that for building frames, we want that the plastic hinges should form at the end of the beam so you can dissipate energy. And so that's your strong column, weak beam. And we don't want shear cracking. We want the flexure because it dissipates more energy. So that's energy dissipation potential we build in the structure. Okay, and how do we do that? We need to have ductile sections. Same thing, we go with and then the columns, we need to make ductile, again, closure and stirrups. We need to make the joints don't fail. And The idea is that even if you have this plastic hinges, the column should be able to safely carry the load downwards. Even the building sways, um, but at least the life safety is maintained. So the maximum drift that we have put something about 2%, so that the structure should remain stable, or not that it has deflected so much that under the P delta effect, it becomes unstable and collapses. So we need to have several criteria that we put in the design, and 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 then we wait for the earthquake to prove that whether it's right, or we have to do certain experiments. So the other option is, if you don't like that drift, or we have better, that primary members should not get damaged, etc. We still have our structure functioning. Then we can have other alternative methods, such as various levels of dampers, friction yielding or yielding dampers, viscous damper, to dissipate that energy and keep the primary structure elastic or near elastic. Okay, for the most of the earthquake, and for extreme earthquake, of course, you may have certain damages to plastic. So there's another alternative way of design. And as I said, for further superior performance, you can also have the base isolation, which provides a kind of a barrier here, so that the energy does not move to the top. So this is a fixed base, but if I put this flexible pads, then I can make this deform and provide a barrier so that the energy do not flow above. So very small movement, better performance, and something like what we had in Bhuj Hospital. Bridges are also being, base isolated, and the premise that you are providing a level beyond which this energy from the ground is not transmitted. Then one step further one can go, that let's say if I do not know about how the future earthquake would be, can I measure this earthquake and then change the property of my structure in real time so that it can resist the earthquakes better? So that brings us to some active control strategy. But meaning is that I have a sensors, they pick up the impending ground motion, and calculate what would be response, and I can have the braces which are active, meaning is that I can make them tight or relaxed, so I can change their stiffness. I can have some mass at the top. If the structure wants to move towards the left, I can move this mass towards the right in real time and create an opposite force to control the deflection. So there can be many strategies, and of course associated problems, because how much power would be needed and whether that power would be available during the earthquake. And remember, the earthquake civil engineering structures are massive. You need a very large amount of power if you want to make any changes. Unlike the other, structures where the active control is used widely, such as airplanes and vehicles, which are much smaller mass and much smaller forces are needed to control them. So in essence, what we're talking about is, that the structure that we have, can be simply represented by the single degree of freedom system as, and then we have this equation of motion for when you have earthquake load that is being applied. This is a mass, this is a damping, and this is the stiffness. And if you just integrate it, and we find that this mass becomes your inertia term or kinetic energy. This is your damping energy, and the stiffness is going into the spring energy, which has two components, something elastic strain energy and hysteresis. And on the left hand side is the energy which is input by the earthquake. Okay. So what we're doing is that we're multiplying this equation with u dot and integrating from. So this way I'm getting an energy equation. This is a force balance equation. and this is your energy equations. So if you see that this is your energy input and this is the total energy into the system. This is elastic energy, so recoverable. This the and spring elastic strain energy is also recoverable. So only two components which are dissipative in nature, your damping energy and hysteresis part. So this is the one which we want to maximize. So that's one way of looking at earthquake resistance of our structures. So as engineer, we try to develop a system so that we can dissipate the energy through damping, either ambient damping or additional dampers, or hysteresis. Hysteresis could be a plastic hinging at the end of the beams. So that's your two components. So you can see here, this is an earthquake and this is how the energy is in total energy input by earthquake is increasing with time. And we need to maximize these two components, WD and WH. And then you see where very little one is your strain energy. So we need to build this energy dissipation potential. Now, how do we test it? Let's say I have built this energy dissipation and then I need to verify it before I apply into the real life structures. So one way is to that we can build, the structure and put it on a shake table and apply the ground motion and see it's. But as you can see, the civil engineering structures are massive. Even moving them, building them in laboratory and moving them requires tremendous amount of power. So what could be an equivalent? If you see this equation here, this is similar to as if the ground motion is applied at the mass here. So we can hold this structure at the ground, and instead of applying the force at the base, we can apply equivalent force at the mass. And we will still have the same equations, you see. So if this UG dot varies in real time, we are simulating the same effect as this one. So this is a moving base, and this is an equivalent force applied at the mass m. Okay. So that's your approach, and that leads to several set of tests that we perform, to understand the dynamics as well as the seismic response of structure. So as I said, you can perform tests in field, you can perform the experiments in laboratory. So the three broad categories here we have loads which can vary slowly, and so we are neglecting the effect of inertia. Then there is a pseudodynamic loads, which are dynamics is word pseudo means that the inertia forces are not on the structure, but rather it's computed in the computers and then transmitted to the structure. So equivalent effect is being transmitted. So this is kind of a combination of computers and or analytical simulation and the experiment. So this is more like a hybrid. And then there are truly dynamic loads, which are your shake table tests or forced vibrations that we apply harmonic loads. So these are the more existing now. In future that we're trying to combine them. Sometimes we combine pseudodynamic with the shake loads in various ways. And because of the equipment, actuators and other things that are getting available, we can have various kinds like real-time hybrid testing, effective force testing, distributed hybrid testing. I mean, these are some variations of pseudodynamic tests, and we will briefly talk about those towards the end. So one important property is knowing the dynamic characteristic of the system, which is basically your natural frequency of the system or natural period of the system and the damping levels. And one way is that you can have some kind of shaker and these are the masses which rotates and so you can have the when they are in the same direction you get a force, and then when they are in opposite direction they cancel out, and again they create a sinusoidal force. Okay, so they cancel, they add, and in the opposite directions, and that's how you. And by moving them at different frequency, I can change. There's the frequency of the sinusoidal loading. So that's your eccentric mass shaker. You can have a simple electromagnetic shaker and then various kinds of accelerometers that you can use to apply a harmonic loads. So that's very simple way. Something like if you're interested in knowing what is the the natural frequency of this temple, which is stone masonry and all that. Of course, you can create some masonry model in the testing in your lab. The modulus of mason mortar and stone. You can create a finite element model, but question is that whether you have adequately modeled. So one way is that, of course, if you know the natural frequency of the system, and that you can measure, and then your model should also show the similar dynamic characteristics. Okay, so here you can take the sensors, and you can do with the ambient vibrations and make measurements, and you can see very clearly that they are short period or the frequency is somewhere in that range, 3.3 hertz, 4 hertz, the short period. And clearly their acceleration control means their stiffness could be small, but they're so massive, that makes them a short period, and they would respond to the acceleration rather than on displacements. But then you have, let's say this, the a half semi-dome, gate as made of the Lakhori bricks and masonry, and they're like 100, 200-year-old structures, and you do not know that what is there. You can make certain measurements about their properties, but and you can create a computer model, but then question is that is it representing the existing structures? So you can carry out ambient vibrations, you can carry out force vibration using those mass shakers, and these are analytical predictions. So as you can see that if you have certain properties and geometry, you can train your model. Now this model can be used for further analysis for various levels of earthquakes, and hopefully your results would be more in tune with with what will happen in reality. You can go more sophisticated with more details, and as you can see that this is the fundamental mode shape. The structure is being a semi-dome, it's unstable in these directions. So this is about 27 meters or tall. So this is more likely the failure envelope, or the displacement, or the modes in which it is likely to fail. The same can be used to train. Here is the 3-story, masonry infilled reinforced concrete frame building, and you can see that we have eccentric mass shaker, then larger electrodynamic mass shaker, ambient vibration, analytical predictions, the pretty much close range. Okay, so now what does it show us? This shows that this building with presence of infills makes this structure also a very short period structures, though we have the a frame, concrete frame, but presence of masonry infills actually makes it to again acceleration controlled structure. So this is what you can see, but this is at very low shaking levels. During the earthquake, of course, the forces would be much larger, maybe the masonry can crack, etc., and then your frequencies can come down. Okay, it could lengthen. The same thing here, our library building, and as you can see that this is the open ground for half of this area here. So these are all very thin columns supporting only the book, the stacks here, and as you can see that this is the 3-story, and the ambient vibration 0.69, 0.5, 0.4 for first 3 modes, and analytical predictions are little different. And the reason is that because this structure is highly unsymmetric, and some torsional and some others which are not being captured very well by this ambient. Ambient means that you start shaking. If I shake from here, this portion does not get, and then you can see there's a large opening in between. So even the experiments, have to be very carefully planned for structures which are of such a high level of irregularity. So very difficult to predict the response of such structures, and that is also, we always talk about in earthquake engineering that we need to keep these structures very simple. Now, so the validation of design is very important, and that for which we are looking at the experimental simulations. So we perform all kinds of experiment for the monotonic, because, and the gravity loads, we apply the load in one directions, and we say, well, we are designing up to this, but let's say if the loads exceeds or the material, how it will fail, then we can continue to load in that directions. So this is something in monotonic testing. Now, during earthquake, the loads reversal takes place. So you go same way, and the similar, reverse in this during the same loading history. So what we're talking about that you load and then unload and then go. So we need to apply some cyclic loads, and that gives us 2 information. First, the loading capacity in both directions, positive moment and negative moment, or positive displacement, negative displacements, positive excursions, negative excursions, and then how much energy it actually dissipates per cycle. So this, remember, this is the WH component. So this WH can be found out from this. If this loop is very wide and full, we have more energy dissipated per cycle of loading. And if these are thin and narrow, then we have very smaller energy dissipation per unit volume of the material per cycle. Okay, so like here is this we come up with that if you have a column is deficient, then we can put angles all around, and then we batten them, and then we can connect it so that the forces that I bring in these steel can be safely carried to the foundations. So let's say this I designed, I developed theory, but I'm not sure whether it will work or not, So this is the column, so it should carry some axial load. So you can see an actuator here, which is applying compressive load, and this actuator here is applying the lateral load. And you're testing half column, assuming that there is a, remember from Portal method that there is a point of inflection at the mid height of the column. So we just isolated an assemblage of the foundation and the half of the column. And then we see that, yes, it's indeed, you can take the load, hold on the load for long, and it works, and it can convert, a weak column into a strong and more energy dissipating column. So let's say you have an idea that we have a frame, and frame as a steel frame, and this is the simple connections. So we need to provide braces for the lateral loads typically. So let's say instead of braces buckling, their energy dissipation is very poor. Can I put some kind of a damper here? And say during the earthquake, this damper will actually yield in shear and dissipate the energy. So what the damper could be, just simply an I-beam. We can take aluminum. So aluminum has the low yield value, so I can use thicker web because this web is under shear and all energy will be dissipated by the web. And so I can use thicker web, because thicker web, then I can delay the buckling which occurs. So if this buckling is occurring beyond my design drift, then I'm okay. So something like 20–30% shear restraint. If I can delay the buckling by using the low yield of aluminum, then I have a good design. So I need to test it. So I just go and say, well, everything remains elastic in this case, the only this thing yields. So I just take out this part and subject it to the sinusoidal load and observe its deflections, shear stress, shear strain, and I can see that is fairly stable up to 20%. So that may be my first step, and this is how I can perform the experiment, and and so you can see that this is a simple experiment in which I'm applying a displacement, a predetermined cyclic load, and then put the sensors here, or measure the shear strain and also the deflections from the actuator and the load. So I can get a hysteretic behavior of this. Now, once you've done it, you can say, well, how this will work for a system. So you can have a column, beam, and then this is so you can say, well, this is my retrofitting scheme, that I have a deficient column. I can retrofit with the steel jacketing and then here I can put damper for additional damping. And then I will put a steel beam which I connect. So this way, this is totally a different system and not disturbing the existing beam, existing column, And I need to have a proper frame where I can put everything, so I can apply just the lateral load from here. So this is the kind of your static cyclic tests. Okay, and so this is the experiment. So we can go on increasing the drift and observing, the performance. There are some vertical load simulations. So the idea is that all the deformation should take place only in this area, and all other members should remain elastic, especially the braces should remain elastic. Okay, so we've gone up to 3.5%, and you can see there's the system was quite well. So it builds us a confidence in these in the systems. And that was a half scale model, So the question would be, well, if it works on a half scale, can it work on a full scale? Okay, so here it is, 5 meter wide and 3 meter tall, full, scale columns, you see. And then you have these dampers here, aluminum dampers, they're connected. And this is at the end of a test. And then there are a lot of loading protocol mentioned that, if you're proposing a system, it must meet, a performance under a specified standardized loading scheme, such as here. And this is the behavior that you can see, that you've gone up to about 20% shear restraint for very healthy loops. And beyond that, of course, there was a buckling of the web, and then the energy dissipation deteriorates. So 20% is kind of a limit for this. And this is the again a video, and this shows you one loading scheme. So this we are looking at from front, and this we're looking from the back side of this device. And this is here the 1000 kilonewton actuator, which is pushing it left and right. And, as you can see that the buckling did not take place at that stage. So similarly, we can carry out. Let's say you develop a new device. In this case, we are developing buckling resistant brace. And our design calls for that aluminum core. And advantage is that it will yield at low, so I can use thicker plate, and therefore I can delay the buckling and get a better behavior. So this is the design that we propose. And then of course there are various loading protocol that if you're developing a device, it has to be satisfy this kind of a loading, going each successive cycle would have 1.4 times of the previous one, and 2 cycles of loading at each of these displacement levels. But then here you have American Institute of Steel Construction. They have a different loading protocol, So you can see now they are also dwelling twice, but different increments. Okay, because different set of people have been involved in developing it. So let's say this is the device that we developed and we built, and this is our casing, this is the aluminum core, and then we are just applying, the axial loads and see whether it meets the criteria that has been set by these codes. So you can see that the aluminum thing is extending and yielding. Okay. Now, what is the difference between these loading protocols? So you can see that more or less they're talking about the same thing, and the behavior was quite good. We can go up to 6% axial strain in these without any buckling, and you can see some strain hardening because post buckling response. So the scheme actually does work. So once we have done this, we thought that can we do a steel in place of aluminum? So we have you can see this, it buckles, and then steel is so strong that the casing which is there to prevent it buckling, that also buckles. So now you need very heavy casing if you're using this steel core, whereas the aluminum is very nice. And you can see that very stable behavior even up to very large deformations. And in the steel, though you get more strength, you can get, but it is do not get enough strain. So that also shows you the comparison between 2 different materials. And some of these can be established only by experiments. Now, let's say where do you want to use it? I would say, well, let's say we want to use in a truss moment frame where the truss is the where this truss is and then you have a column, and here I'm using as a knee braced, this link. Okay, and we can test only this portion, because there is going to be a point of inflection here and point of inflection here. So I can just take this portion and test in the lab. So this is what we're doing. Here is the point of inflection. There is a column, could be on second story. So there is a column here and point of inflection, which represent this point, and there's a one and this point. And then this is the brace, and this is your truss. So the idea is that if I apply this horizontal load here, which is the same as applying horizontal load here, vertical load here, which is equivalent to applying horizontal load here. So create a sub-assemblage, create the proper displacement and force boundary conditions, and then we have to demonstrate that, the entire the truss and that the columns should remain elastic um, for the design forces or design drift, and only the braces buckle or yield. Okay, that's the once you've done that, of course, you need to perform experiments. This is another set of experiments. 2% drift, the system is more or less elastic. So these are the ways in which a new system that you develop can be verified, and experiment is the only way. These days people are using the AAC blocks, as infill material. Now question is that is AAC infills are better than the clay brick? What would be its impact on the if you have the open ground story frame buildings, will be the ACC blocks are better compared to the clay brick. So you want to carry out this analytical or fragility analysis of these systems, but then you must know that how does the frame behaves with the AC infills, you see. So again, if we can perform an experiment and if I know what would be its hysteretic response by using this, I can actually develop the fragility curves and similarly I can develop for the clay brick and can tell you that at different loading levels what would be its the differences and which one is better. So again, generate this, you need to have a frame, you need to place walls, and then you apply this the sinusoidal lateral load to generate the force deformation relations. We need to go at least 2% drift because that's the minimum that we now since we're doing a sub-assemblage, you should do a little bit more than 2%. Now you could have seen that how the behavior was, it is much better uh, than the clay bricks, but visually it's okay. Similarly, for any systems, let's say you have the confined brick masonry system as the people have been building in many earthquake prone regions such as Kashmir, etc. And you want to study that what is the force deformation relations. There's why they do better. What is their nonlinear response? Go to the elastic. We can build the specimen in the lab, subject it to the gravity loads, and we can obtain the hysteretic response. As you can see here, that this can go up to 1.5% drift, you see, and even maintain significant, you know, uh, strength, even up to 2.5%. So what is this doing is because it's the 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 timber which is there in that they subdivide this wall panel into smaller segments, and there is this uh, what you call is the preferred sliding plane along which this masonry moves along and dissipates energy and imparts the flexibility. So it's from choosing the arrangement, you can see that what is good for you, So now we have performed the experiments. You can model in a Bacchus, can get better insight. Once you have that, then you can develop some design equations. Like here, what we've done is the confinement parameters, that how much more interior members that you have compared to what we need just to confine from outside. And if you have just only horizontal and vertical, it's the strength, it increases, much less. But if you put the diagonals, then the strength goes up. So you have some data from the experiment, and others you can do with the finite elements. And similarly, you can do with the stiffness. As you can see, the horizontals don't add much stiffness, but verticals add more stiffness. So these give you some idea about how the, if you want to design, this confinement, how much extra elements are needed. These days, people are providing this, the, hollow large beam openings to pass the services. Okay, and question is that, if you look at none of the, the codes actually advise you to do that, and especially the one which is resisting the earthquake forces. And then there is a lot of severe restriction that how much opening that you can provide. And you can see that not in this beam, but there are other beams in the same building which were too many openings were provided, and some of them very large, and that led to the cracking in the gravity load itself. I mean, just after removing the formwork. Now, we wanted to see that if somebody has to provide the opening, then how much and how these members, which are at the top and bottom, which have to take these forces, which is basically the shear forces that are there because of the opening in the web. Okay. So we developed some scheme that how these members need to be designed, what should be the reinforcement at the top and bottom. But we wanted to test it to know that our design scheme works well, because according to our earthquake resistant philosophy, we should not have anything, inelastic activity taking place here. The only thing that is allowed is some plastification at the end of the beams. Okay. So this is the half-scale specimen constructed in the lab. And again, we have to test it according to the ACI 374 loading protocol, and going up to all the way up to 2% drift to see that whether the system is doing well. And this is at the end of the test, you see. So you can see that this opening, this design was perfect, and you have the plastic hinging at the end of the beam. And since this is only one column, then of course there are some damages here. But this is very large, 4.9% drift. Okay, and you can see fairly stable behavior. So if you can have very small openings, and that also located significantly away from the column ends, and then sufficient reinforcement at the chords, at the bottom and top chords of the opening, then you can have, these openings even in the frame which are resisting earthquake. So that's your pretty much a static test that I talked about in several applications. Now, the equation of motion was like this, so we are only concerned about getting this load displacement response. Okay. Now, how about the two other components, the inertia and damping, and then the real earthquake? So what I can do is I can create a mathematical model in the computer and solve this equation, okay, and find out what the displacement should be, and that I feed to my actuator and then displace this structure, measure the forces, and then modify this K again, and then solve for next step, and that way I can continue doing it. So now in this case, I would be calculating this inertia forces and damping forces in the computer. Their effect is calculated analytically, and the new displacement is calculated and applied to the structure, and then next step. So step by step we are simulating. So we're not doing real time. As the earthquake, let's say, is 20 seconds, we may take 2 hours to do this test, but in a way we will be compensating, for the effect of damping and inertia, and that is called pseudo testing. Okay. So here is the, let's say, this same knee brace TMF I had, and I want to verify it for the Taft ground motion. Since we are doing scaled, we need to reduce it. So we need to make certain modification into the ground motion also. So we compress it because of the similitude requirement. And we choose this Taft ground motion because it fits very well our dB responsive spectrum for which the system has been designed. And this is the specimen that we built. And let's see if this works. You can see that now we're not applying the cyclic load, but rather we are applying that earthquake. Okay. And these are the 4 our knee braces that you can see them moving here. And we are applying 3G Taft ground motion. So this is 5 times of dB. Okay. And then, we can run each. So you can see this is the half of the dB, 10% dB. System is elastic, almost at MC level. There is some little bit of yielding, and as it go further and further, you can see. And if you notice that the structure actually starts from there, get displaced, and then never comes back because, and so this way we can have a confidence that how much is the reservoir strength and how good this system is. This is another way of measuring that what was the actuator load that we measured and what was the I calculated from my computer, and it follows very closely, meaning is that we are simulating this earthquake effect, inertia effect, very, very, very close. Now, as you can see in this test, that you need to have a very large, if the specimen gets bigger, you need a large reaction wall to support the load and push this structure. And all the major labs in the world have such, 2-3 story massive walls to push this structure to the ultimate, So at the IIT Kanpur, we also build a wall, which is, 10.5 meter high and almost 2 meter thick, and so we can test, pretty much, 2-3 story buildings and the bridges of 15-20 meter length, So we can apply 1.5 meganewton load and shear and 2 meganewton and axial at each of these anchor points, which are located at 2 feet. So, and the force rating of the system is, typically how much moment it can resist, without any appreciable displacement. And that in our case is about 10 meganewton moment for each 0.6 meters. So these are some pictures showing the construction of it. This is the, as I said, the pseudodynamic testing is a cheaper version of the shake table tests. If done right, you can get the same set of informations. And these walls are pre-tensioned, post-tensioned with the same cables as we do in the bridges. So you can see that all the post-tensioning so that we can get more moment capacity for these walls as a cantilever. And you can see that the layout, and this is the reinforcement for the columns, the normal reinforcement. And then this is how the structure was finished. And the first test that we did was I just presented about that frame with the beam openings. Now, this is not only limited to the size, so that's what we refer as the hybrid testing. So you can test a portion of the structure in real life in your lab, and the rest can be analytical. So the way we can do is we have our equation of motion. We can actually divide or partition it, something which is an experiment, something which is analytical, and that way we can also do it. So there are various possibilities. Now, if these actuators are coming, which can move in real time, so then we can run these, in just the 20 seconds, whole earthquake we can do as we do in the real life, But for that you need very fast computers and very quick response actuators. So something which is limited we can do at smaller force levels, but not at large level force. But in future, you may get the actuators which can move in real time, and we can do this real time dynamic tests. Now, other is your shake table test. This is that the Rudke shake table, which is set up in mid 1980s, and 3.5 meter is a biaxial 15-ton, very nice shake table. And however, as you can see, it's a 15-ton, that's a payload, so we can only test very small scale specimens. And but the largest shake table that we have is the setup in Japan, which can take 1,200 tons. And you can see that it can go maximum acceleration 1g. This velocity is very important, 2 meters per second. Because if you see the 94 or 95 Kobe earthquake, there's a lot of damages because the velocity of that earthquake motions are much larger, somewhere between 1.5 meter and above. So they wanted to build a shake table which can have the maximum velocity 2 meters per second and displacement 1 meter. And I can see that how much this 24 450 ton actuators, and this is the so the total power requirement to run this could be more than something that requires to power many cities. Okay. So the first thing that they tested is the timber frame, because those were the one which is badly damaged. Now, analytical simulation modeling this timber and joints is very, very difficult, but then there's experimental verifications and data not only helps you see that how the structure failed, but also train your computer models. And of course, you can have soil structure interactions, soil water interactions, and many other things on such large table, but they're very expensive. Now, at the IIT Kanpur, we have simple uniaxial shake table, which is a stainless steel platform, something we assembled. We had this is what we built so that the platform should be rigid, so it should not move. And you can see this the grid work of plates, and the top and bottom plates are stainless steel. And again, we also wanted it to have very high velocity, but the uniaxial payload is only 4 ton. And this is our control. So you can see that this is the ground motion that we are mimicking, and we are very close, and this is the match of the responses spectra. So this is the table performance that we are able to get 1.5 meter per second here, close to this. And then, of course, as your frequencies increase and decrease, then you have a fall of your velocities. So you have to tune it to a certain. So now we've been talking about this, our aluminum shear link. So you can say, well, can we test it on a shake table and see if that works? So here we are using a very one 1/12 scale model. So you have very small shear lengths connected, and then this is the artificial mass simulation, the mass which is attributed to this particular frame, and here is the response. So if we are elastic, if there were no dampers, then the response is something like this. This is the maximum base shear increases with as you increase the PG of the ground motion, same Taft motion. But if I put the dampers, then it is a blue line because it starts yielding and does not let the forces increase beyond that, and it buckles and yields. So this is something you can do for proof of concept tests. You can design it appropriately and following all the simplitude laws, something so then only the forces and the resistance will be proportional, and you can observe the behavior in the more. So this is the Taft motion. We had 1.6G, and then we're running the white noise to find out the dynamic characteristic of the systems. And this is something at the very end, and now you can see this. We're able to simulate the buckling of the web, and you can see this. The braces remains elastic. So of course it does not. By looking at this, this is not of your typical building braces, building system, but then it's a proof of concept tests, and probably this video is not working, but we have another setup, for the the truss moment frame, and you can see that if the normal TMF without the damper will have this response, okay, and with the aluminum shear yielding, you can see that it starts yielding, and it no matter what the acceleration levels or base shears are capped, okay, because you are dissipating that energy. And here are the comparison between their time history responses. You see, so you can see with this damper, your acceleration levels are way lower than what were there if there was no damper. So and there are two sets of tests we did. One is your stick table test and one is your pseudodynamic test. And here is the comparison of these two tests. And you can see that they follow very closely, and these are the time histories. So in one way, what I'm trying to show here is that pseudodynamic test and stick table test are equivalent. Okay, if you do it right, they will give you the same result. Okay, and the pseudodynamic test being much cheaper, than the stick table test, and you can build a larger specimen and test it. So the same thing can be done for many a system, for masonry walls. You can combine, the shake table test for out of plane loading, in plane test for the actuator loading, that as we talked about, and you can employ the shake table for the out of plane, as in this case, and for the in plane, you can bring in the frame and immobilize this structure in this direction, and then apply the lateral load, and then you can do a particular loading program to study that what happens if this wall gets weakened under in plane motion, and how the out of plane forces will affect its response. Now you see this little dots that are there. These are actually lead blocks that are created because we're using half scale bricks, So half scale bricks, we're just reducing the geometry by half, geometric dimensions by half, but then the volume goes by 1/8. So inertia forces also gets reduced. So we have to bring up the inertia forces to compensate for that loss. So I need to have a non-interactive mass, which does not add to the stiffness, but add only to the mass. So that is how these lead blocks are done. And here we need additional mass need to be added for each brick, which is equal to mass of that brick. So in this case, we are adding one block is actually 0.865 kg, which is compensate for 2 bricks. So then you calculate it, you attach, and this is a few videos just to maybe show you the difference, what the internal elements can do. So this is half scale model, and you can see very only boundary elements are there. So if somebody is looking at it, it will calculate the H over T is this is half a scale of your 3-meter wall and 5-meter, and this is the, so you can see that it can go up to only damage state and barely damage and collapses. This is what happens. But let's say if you put some interior member here and subdivide this large panel into 4 small panels, so slenderness ratio gets reduced by half from this point to this point. And we apply the same loading program. We apply 0.5% depth, typically the masonry cracks at 0.5% depth. If you push it further, you get more damages. And now you can see the damage is more distributed to all 4 panels. And we've gone up to 1.4% depth. Still, this masonry is inside the frame. Of course, you can expect some cracking way down there. And let's see. And this is 2.2% drift, something that we expect in all frames. And still the frame, the masonry is inside the frame. So we just applying with minus harder load, just a catastrophic load, just to see that, whether we can somehow push this masonry out of the frame. I mean, that you'll never have an earthquake, something like that. So this just shows you the effectiveness of the, interior members, And then there are many other techniques, people are coming up with, to improve the out of plane resistance of the wall. One is your this fabric, glass fabric, a textile, and then you can apply directly onto the masonry walls and cover it in a plaster, or you can have a 1 layer of plaster, then put it and then finally finish with another layer of plaster. So that was sandwich applications, or having this mechanical anchor so they're attached. And you want to see that how effective this is. Once again, we need to perform some set of experiments, and this is showing you, uh, you know, assembly. Is a new role out of it and out. So this is the way, but what if I provide this text now? have not written yet, but bed points like accepted when you have a strong important is that not getting out of the frame. You can't have out plane collapse of the wall. Okay, even at such large drift and can associated damage. So this leads to your confined masonry constructions, which is also very common, where you have the masonry is raised and then the column is filled up. It's very common in most of earthquake prone, and you can evaluate that whether you want simple infill or what this confined masonry does it. So maybe yeah, uh, model and the way it's sliding often that oh, that it can be pushed out. That you see that this portion is can fall out. Now here is not like no separation at assembly concrete interface, and we're going to vary 1.75% drift. So, and so out of plane resistance, and this is one reason that why they do better. And even if there is openings, you see that um, their performance is much better. Your is the end of the video. Self infill constructions, down the openings. It's that this speaker shares uh, however, this is spandrel masonry is not what. So one could expect that the damage would be mostly centered around these openings and the door, maybe the windows, if they get started, etc. You may not be able to open after the earthquake. So there are many, and the stop this video just to get an idea that how the damage will be. Remember, this is the damage level, but if you can find it's that tears or strengthened by the boundary of the heights and out of it. You can see with the masonry below the openings are being worked up. You can see by sliding, and therefore you can see that. And then distortion of the openings that it goes, chances that it goes after the other uh, this, and as far as out of plane integrity, that is very much in. We are now at 1.75%. So we run out of the our density in red. So now we are able to achieve the same level of permeability as well designed ductile and and we are applying 2 times of the ozone fibers for 60 times, and still this the so that actually proves that how this confined masonry wall, even with the openings, they can perform better. So you can read more about some of the papers that we published, and that shows that here you can see this is the solid confined masonry wall, which is in the red, and this is the one with the openings. You can see that they reach at the same peak and able to be more ductile. So compared to this normal infill masonry, which is loses their strength much faster. And no wonder, there are many places where people are now using confined masonry. This is one of the last, you can use these experimental techniques even for these non-structural components, like your suspended ceiling these days are becoming more common. You have plastered board ceilings, which are just one unit or several ones are added together, but they're hanging from the various configurations. You can have just vertical, or you can have vertical and braces, or or it can be connected to the wall all around, or fully suspended. So question is that which one is better, which one is more you know uh, so we tested 4 such configurations, and this is the test frame that we had. So this is our SEC table on which we put this somewhat very rigid system, on which we create a 3 meter by 3 meter frame. And this is the ceiling can be suspended. We make it rigid so that we are assuming that the walls of that room are rigid, or like infill walls, and then they are suspended from the top. The top members are out of plane, is adjusted so that they have the same natural frequency as uh, typical floors, and then they're hanging this suspended ceiling. And we can, since we have a uniaxial, we apply the load once in the short direction, then we rotate and then apply in the long directions, and that way we can perform set of tests just to see that when it starts failing down. So this is the setup, and then we can put all the sensors, etc., measure strains in the suspenders and everything. And then we keep increasing to the further levels, you see, and so, and then we can have all the recordings. We can see that what was the response when there was no damage or more damage. These are the last one we're seeing fully floating. So fully floating has at the 0.7 GPJ, that's the last one that you saw, has much more displacements, etc., compared to the one which are have other members, free fixed all around. That is the best system. Then free all around, and but the braces, they're as good as the fixed all around, and free all around suspenders, but the fully floating are the one which are the real really bad. So then we can, once we have this, we can train our computer models, and then we can do for many other earthquakes. So as I said, there can be a real-time hybrid. We can have a SIG table, and then you have this pseudodynamic, and then and rest is going into the computer simulations. So people are trying various ways so that we can understand our structure better. This is the first test done at the initial phases where people are thinking, can we do the experiments at several locations? At one place you have a physical substructure is being built. Let's say this is the structure that you want to investigate, and this one is experimental part. This one is your mathematical, and this is another experiments. You see, and they are being run through over the internet. And what happens that 15-second ground motion was completed in 5 hours, So that is because of your communication over the internet, you see. So somebody had analyzed this on the computer. So you're taking the input from this one end, putting it and solving it, and then supplying it to the other end and then you're running these 3 components of the same structure at 3 different places and in 3 different modes. 2 are physical and 1 is numerical. Okay. Likewise, so if you see in the future, there's things that are happening. Conventional wired sensors are being replaced by wireless and non-contact sensors. We have techniques to measure the full field displacement field or strain field. We can synchronize our visual images with the data, because we can stamp it and we can play it back. And what it does is that way, few experiments are done, but you can have the information and people can play it back online, and you can have the same feeling as if watching it in the laboratory. So these are the areas in which people are being active to do more experiments. So since our focus has been on an earthquake, in the end, I would like to say that, you need to build earthquake resistant structures, but doesn't mean that, we have the only methods which people have used in the past. We can have newer methods which can give us better performance, but these novel techniques need validation, and that validation can come from physical tests as well as analytical simulations. So physical test, I say that they should be low cost, and analytical simulations have the higher resolutions, because they're cheaper. So we can do high resolution here, but some physical tests are needed, so that we can train or test our analytical simulations. So this is one reliable and effective method to study the behavior of a structure as a whole or any components. And as I said, there are more methods are being discussed coming up, which can help us understand the structure better, and therefore we can build more efficient and safer structure in future. The last slide. This is not our experiment, but experiment done at UC Berkeley on their large SIG table, which is just showing us the success of design, meaning is that we have a ductile column for the bridge. So this is the circular a ductile column as we know in late 90s, on both ends, and in the middle we have a non-ductile column, as was done in before 70s. You see, when the provisions of ductility were not developed, and this is, you can see the rectangular column, and this is your cap beam over which you can expect the deck to be here, and deck is simulated by the huge stacks of lead blocks. Okay, so these are non-interacting dead loads. Okay, so when the ground motion is being applied, this is going to impose the inertia forces. Okay, so let's play this video. Yes, great. So this is the way, and of course you can see that a design can be tested, on the experiments. Okay, and for every occasion you can find a quote, and I also found one quote which says relates engineering and laboratory, and they say engineering without labs is a different discipline. If we cut out labs, then we might well rename our degrees as applied mathematics. So that is the all from my side, and thank you very much. And can we just stop at this slide and see if there are any questions? So
Yes, sir. Thank you very much, sir. It was a really wonderful and informative session for all of us. Each and every concept was touched in a well-organized way, which helped every participant to enhance their knowledge. You make us clear with various important topics like dynamic characteristics for load deformation behavior, future train test, slow cycle test, strengthening of non-ductile RC frames, PSG test, pseudo-dynamic test, and confined masonry test. Sir, I would like to request you, can you please share your presentation with us? Because it will helpful for all the participants for their reference. Hello, sir.
yes, that's fine. Well, you already have the
Okay.
made, so that's good enough. But we'll see what we can share. Yes.
Okay. 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 So now, if you have any query regarding this session, you can ask all participants. Please raise your hand if you have any query.
Uh, Sir, as far as testing is concerned, uh, what should be the means how we decide the acceleration to be applied for the shaking?
Well, I mean, see there. what we're trying to do is that if you just want to test for the dB level, so you can test it for, zone 5. Let's say that is what I want to, design my structure for the most severe zone. Okay. But then I can perform the experiments, what we consider as incremental dynamic analysis. Like say I apply the design level force, okay, and if nothing happens to my structure, then fine, I know what the density result. Then I increase it to a higher level, and so keep on doing it until the structure collapses. So that gives me the idea that how much is the reserve strength it has beyond the design. Okay, so there are the 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 approaches, to know the reserve strength. So if you design, let's say for the zone 5, then the acceleration levels is 0.36 g. Okay, but then you're designing for half of that, the dB, that is what you provide. So I will start with the 0.18 g, or maybe even I start with lower than that. Okay, so I can see that what is this elastic response, what happens if there's a design level earthquake, what happens when it goes higher, 2 times of the design level earthquake, 3 times design level earthquake. So keep increasing the intensity of the ground motion till it fails. And we need to know always the failure mechanism of the structure. Then only we can design properly. So though for the structure should remain elastic, or the expected inelastic behavior in the design earthquake. But for the larger earthquake also, we must know that how the structure will behave, isn't it? So acceleration level is not that important, because that is what we are varying for the intensity of the ground motion. Okay.
Okay. And sir, you said that that is a the test was performed at 2 meters per second, which is a very high velocity. Uh, so, what should be the ideal range of velocities that is to be taken into consideration when from the test? Uh, if we go for the lower velocity, uh, then how it differs from the high velocity test?
Okay. Well, this ground velocity depends upon the nature of earthquake motions. Okay.
Yes.
So, like the Kobe ground motions, if you see, I mean, they have pulse type motions. Okay, in between. So they have very high ground velocities, but and that could be a reflection of the nearness of the fault or the nature of the faulting. You see, so the point is that the damage is more correlated with the velocity. If you see this, the uh, Nepal earthquake, the kind of the damage that took place in Kathmandu was kind of disproportionate to the level of accelerations. Acceleration was only 0.2 g or so, but the ground velocities were something on order of 1.2 meters per second. So so you need to have a sig table which can, at least have the velocities of order of about 1 meter per second, to generate or simulate these damaging earthquakes. But even if you do not have, you still can play El Centro, which have the much lower ground velocity and can understand the effect, you see. So I wouldn't say that, if you do not have a stable which can generate this much velocity, then it's you cannot get in, information. As I said, this is matter of training. So once you train your numerical model, you see that for some level of dynamic characteristic, etc., then many things can be played out in numerically, So once you're developing the new systems, you have a lot of unknowns about the model. So once you make a computer model, you may not be able to simulate, or your simulations may not represent the reality, and therefore you need to make sure that it is representative of the real life behavior, you see.
Thank you, sir.
Mhm.
Good afternoon, sir. Myself Nitin Kataria. Uh, just when we are doing the testing of shake table, if we are doing bidirectional or tri-directional testing, should we have to consider all earthquake in its full form, or we have to utilize the like given in the IS code that 30% like that one?
Well, I mean, you can do either way, but what is more realistic is, what more realistic is that you pick up any ground motion, okay? And that ground motion has all three components recorded. You have both X, Y, and Z, So I would actually play that real ground motions, if I want to know what my structure will do in that. But if I'm testing whether my design as per the code is okay, then I need to apply a code level ground motion, isn't it? So in that case, I will say, well, let's pick uh, the horizontal motion, which is the strongest of all three, strongest of the two horizontal motion, and then take 30% of that in the other directions and the vertical. So that I'm testing for the code compliance, okay? So it all depends upon what is your objective of the testing is, okay? So, in reality, that doesn't happen, that the other component is going to be 30%, this is something what the code, approach, because the code is only giving you one ground motion and then saying is take the certain proportion for the other directions, So it all depends on your objective functions. See, if you're looking at the code compliance, then probably they would like to see that it is 100% in one direction, 30% in other two directions.
Thank you.
Sir, in few of the slides you mentioned white noise. So can you elaborate on that?
Well, white noise tells you that it has the same energy at all frequencies of loading. Okay, so this is little something in it. If you see the real earthquake motion, the energy is not constant. Okay, so at some time, it will have more energy in other places. It has a smaller energy. So what it means is that you are exciting that structure with a different intensity at different frequency levels. Okay, so white noise is artificially created, uh, uh, what do you call a sign, a signal which has the same energy throughout its frequency band. Okay, so what we are trying to do with this, why we are using the white noise, because I want to find out what is the natural frequency of the system. So to know the natural frequency of the system, I'm actually exciting it, to with the same power, same energy, at over a range of frequencies. And the one, which is this natural frequency, I will get a larger excitation. So that's how I pick it up. This is my natural frequency of the system. So that's the purpose of the white noise, to have the same level of energy over a range of frequencies to which I want to subject my structure. Okay.
Okay, sir. Thank you, sir.
Okay, thank you, sir, for answering all the questions.
Okay, good. Thank you very much.
Now, I guess no one has query regarding this session. Thanks again, sir. Thank you very much for such a great session. Now, all participants have a reminder for the second day of the training. I repeat, it's a reminder for the second day of training. Session 1 will be conducted by Dr. Alpa Sheikh from 10 to 11:30. Session 2 will be conducted by Dr. Rupen Goswami from 12 to 1:30. And session 3 will be conducted by Dr. S.T. Bharti from 2:30 to 4. I hope all the participants enjoy the first day of the training, learned something useful and interesting. Thank you very much.
Thank you, sir.
Okay, thank you.
Thank you, sir. It was really wonderful lecture.
Thank you. I feel like it. Okay. Good.